Thank you for that, and thank you for the kind introduction. Yes, we don't have a full room. It reminds me of one of my statistics lectures, so I feel at home. Oh, what's this? I'm registering my software here. Okay, so as Stephen said, I'm going to talk about a nice, basic, generic topic. So it's not going to be particularly couched in terms of HIV medicine, which is lucky because I don't know a lot about it. I'm a non-communicable diseases type of guy. So I'm going to talk about statistical inference, traditional ways of doing it, which aren't particularly informative, and newer ways of doing it. This is not cutting edge. It's just a little bit of a change in the way we think. Okay, so the main role of this session is to try and dispel some of the myths that we have about how we should talk about significance. And I'm going to discuss that word significance in a lot of details. In particular, I'm going to focus on the use and what I see as misuse of the p-value in clinical research, and highlight a much better way. And by the way, I mean, I didn't come up with this. This is well-established methods for talking about the significance of our results. It's, as I said, it's just a bit of a change in the way we think. And this is something that I guess statisticians are trying to push a little bit more these days. So I'm going to talk about p-values. I'm also going to talk briefly about sample size, because sample size is very, very important to the notion of significance. So the first thing I'd like to do is actually just change the title of this talk a little bit. I'm going to talk about it as statistical inference in medical research, p-values, effect size, and confidence intervals. Okay, I thought about this recently, okay? And I worked out, I did a little quick calculation in my head, and I worked out that I've probably provided input into about 10,000 research projects in my career, which is a horrible thought. It actually made me unhappy. I want a holiday. I want to retire already, okay? That was the first thing I came up with. But one of the things I notice a lot is that many people have misconceptions about some of the statistical rules and conventions that are used, why we do what we do, and why we use statistics in the way we do. Why is this the case? I think probably the most likely explanation is that most people don't like statistics. There's a lot of fear and loathing when it comes to statistics. I'm not sure if statisticians are responsible for that, but it is what it is. So many researchers I've noticed, and this is especially the case with the early career researchers, those people just starting off in research, view statistics as a hurdle. It's a hurdle to get past. I'll just follow the rules. I can get past it with the IRB or ethics committee. I can get past it with the reviewers. I don't want to think about it, okay? And that's one of the things that leads to these major problems. It's actually not that hard, at least the parts I'm going to talk about today, why we have these conventions. Understanding these conventions, if we can think about it just a little bit, it makes a lot more sense. So this, I guess, pragmatism when it comes to statistics, so a hurdle that we have to jump over. I just want to use it. I just don't want to do it. I don't want to think about it. This pragmatism, it really does come from, I believe, people remembering these rules about vaguely from the dark days of their undergraduate statistics courses, and we talked about this before, when we should be trained in statistics. And what it leads to, and I do see it a lot. I would probably guess around 75% to 80% of people that consult me, I see this attitude. Just follow the rules, don't think too hard about it. Okay, so we have these conventions okay? We don't know where they come from, and we believe them, okay? And I guess what this leads to is a little bit of pseudo-scientific religiosity. In other words, thou shalt reject the null hypothesis if p is less than 0.05, okay? Not understanding the reasons why, and that's just a little cartoon. I'm not sure if you guys are familiar with, everyone will tell you cockroaches will survive a nuclear explosion. There's no evidence to suggest that at all, but everyone seems to believe it, okay? The p-value is less than 0.05, means something is important, is exactly the same. Well, not exactly. It doesn't necessarily mean it's not important, but it doesn't necessarily mean something is important. Okay, so what do we mean when we say something is significant? It can mean two things. So there's a lot of ambiguity with the word significant. It can mean our result is statistically significant. That is where p-values come in. So it means an association or difference or effect that we observe is unlikely to be due to chance. That's what it means. And really, that alone, that's all it means. Alternatively, our result might be clinically significant. And what that means is our observed effect is important. So for example, our treatment leads to substantial benefit in terms of patient outcomes, or a prognostic factor might give us considerable information about how a patient's prognosis. Okay, so that's important, okay, as opposed to unlikely to be due to chance. These mean two different things. The problem is we use the same word to talk about these two quite different concepts, significance. To avoid this, I tend to use the word statistical significance and clinical importance to separate these two quite distinct concepts when I talk about these types of things. So statistical significance is about whether an association is real, or did we just dream it? Are we just imagining it? Okay, so traditionally we've used p-values to gauge statistical significance. So if a p is less than 0.05 by convention, we will conclude that our result is statistically significant. The problem is what does this really mean? To understand, I guess we have to think about the formal definition of a p-value, which no one really ever thinks about. I mean, I don't even think about it that often myself. So what is a p-value? A p-value represents the chance of seeing a statistic, for example, an effect size, as extreme by random chance alone. That is, if the null hypothesis is true. So, for example, what is the chance of seeing an odds ratio of remission 2 times higher in the treated group relative to the control group if the treatment really doesn't work at all? What's the chance? If it's very unlikely, we throw away the assumption that the treatment doesn't work. We reject the null hypothesis. Okay? So, by convention, if this chance is less than a 1 in 20 chance, the null hypothesis, we can't keep it anymore. We have to throw it away. Okay, and that's that idea of rejecting the null hypothesis. However, one of the problems is that statistical significance does not necessarily imply clinical importance. Often they don't match up. Why? Usually sample size. Sample size is the number one thing that disconnects statistical significance and clinical importance. If our sample is too large, we may see a statistically significant result that is not clinically important. It's clinically trivial. If our sample size is too small, we may see a clinically important effect, but we don't know whether it's going to hold for our population. It might just be in our sample. Okay, so it could be something we just dreamt or imagined. Okay, so if sample size isn't about right, statistical significance and clinical importance don't match up very well. So one of the most important reasons for conducting sample size calculations is to try and align statistical significance with clinical importance. We want to be able to say, if P is less than 0.05, we're observing a clinically important effect. So think about sample size as a calibration process for our statistical analysis to reality. So we have a solution to our problem, don't we? Sometimes. The problem with formal sample size calculation, and I'm talking about those little Greek letter formulas that we see and that we hate, is they only really work well in quite simple situations. For example, randomized control trials. That is an analysis that can be done using simple bivariate methods. As soon as we start going to observational cohort studies, where we need multivariable modelling and there's a complex interplay between all our predictors, there's confounding effect modification, there's all sorts of horrible things going on. The problem is we don't know before we conduct the analysis how to fit all of this into a formula, and these formulas don't really exist. Not well, anyway. They don't work well. How do people get around this? They often trick their institutional review board or their ethics committee. That's how they get around it. They put the simple formulas in and they make up some numbers. It looks like good science, so therefore must be good science. Okay? That's not a good approach. It's not a good approach at all. And I'm going to say something that should be quite obvious, but isn't. Sample size formulas. Okay? And we have to remember, there is more to good science than Greek letters. Okay? The right sample size formula with the right numbers will give us the appropriate sample size. The wrong formula with the right numbers in it will give us the wrong sample size. Sorry, I said that the other way around. The wrong formula with the right... No, I didn't. Sorry, I'm confusing myself. How am I going to convince you? The right formulas with the wrong numbers is going to give us the wrong sample size. And here is the most common one I come across. The wrong formula with the wrong numbers. Is that going to give us the right sample size? I don't think so. Okay? So sample size is something, and particularly in observational studies, it's a very vague guideline. Beyond that, that's all. I mean, really, we have to give it... we really have to assume that it's not going to give us the right number. It's a guesstimate. That's what it is. Okay, so I just want to check you understand what I'm talking about with statistical significance and clinical importance. I'm going to give you 3 examples. I haven't used HIV because I would have had to have made up things. I would have come across as an idiot. I don't know much about HIV, so I've stuck to what I know. And in fact, I've been as generic as possible. So let's go through the first situation, okay? And I want to talk about this disconnect between statistical significance and clinical importance. In the first case, our outcome is all-cause mortality, okay? So we have done a survival analysis. We have a hazard ratio as our measure of association. A high-fat diet leads to a significantly increased risk of mortality. Those on a high-fat diet have 3 times the chance of death relative to those on a low-fat diet. The hazard ratio itself is 3. The confidence interval is 0.8 to 8, and the p-value equals 0.25. What's happened there? Is a hazard ratio of 3 clinically important? 3 times the chance of dying. Do you think that sounds important? Yes. Is it statistically significant? No. What do you think is a likely explanation for why those two things don't connect? Sample size. That's exactly right. We've probably got a sample size that's too low. There are other explanations too, more variability than we anticipated and so on. But sample size was probably too small. In other words, we saw an effect size in our sample, but we can't infer that to the population, to our population. Case number 2, systolic blood pressure as a continuous variable is significantly higher in men than in women. The mean difference was 23, and we have a confidence interval of 7 to 39, and P was less than 0.05. Is it clinically important? Yes. Now, you need to know something about systolic blood pressure, don't you? You have to have some clinical knowledge to assess that. It's clinically important. Is it statistically significant? Yes. So it was unlikely to happen by chance, and we believe that what we observed in our sample flows through to our population. Okay? That's right. So that's relatively strong evidence, providing that the design is good and so on. The third case, blood pressure control. Yes, no. So a binary outcome. The odds of blood pressure control is significantly higher in females relative to males. We have an odds ratio of 1.05. Okay, so 5% higher odds in women relative to men. There's our confidence interval, 1.02 to 1.2. P is less than 0.05. Statistically significant. Unlikely to be due to chance. Clinically important? No. What's happened there? Sample size is huge. We may have a very large sample size and we can say it's statistically significant, but it doesn't seem to matter that much. Okay? Being a female isn't particularly protective, okay, in this case. So that's it. There's a disconnect. In case number 1 and case number 3, there is a disconnection between statistical significance and clinical importance. Okay, and we've already answered how sample size comes into it. So if only there was something we could do about this complex relationship, a mess between sample size, statistical significance, and clinical importance, particularly in this complicated situation of observational studies. There is something we can do. First of all, we can understand what it is we're looking at. Okay? We can insist that an author produce effect sizes and confidence intervals, not just p-values from chi-square tests, for example. So this provides a more thorough disclosure of our results, allowing a reader to gauge whether we are providing results with strong evidence. So how do we gauge effect size? Well, it depends on the type of outcome we have. Typically, not always, but typically for continuous outcomes, if we're comparing groups, we'll use something like a mean difference. If we're looking at the association between two continuous variables, we might use a standardized beta or a correlation or something like that. Binary outcomes, we use things like odds ratios or differences in proportion, again, depending on design, which is better. For time to events, hazard ratios, there are other things as well we can use. Counts and rates, we can use rate ratios. Now, the one thing I would say is odds ratios, hazard ratios, rate ratios, we can interpret in a similar way. Not exactly the same, but in a similar way. So effect sizes provide a good idea in terms of the variables, the outcome variables we're actually using, about the magnitude of the effect we see in our sample. But we also, that's not enough alone. We've seen this already. It's not just the effect size itself. So an odds ratio, for example, we need a little bit more. We need to say, is it a good estimate? Is it a good estimate of reality? So to gauge this, we will use confidence intervals. So a common misinterpretation of the confidence interval, and I find I do this myself even actually, is that a confidence interval has a 95% chance of containing the true population value. Strictly speaking, that is not true. It has a 100% chance or it has a 0 chance of containing the true effect. But it is still a useful analogy. And I think what we can do is provide a simplified statement. Operationally, we can view the confidence interval as an estimate of a range of plausible values for our population effect size, okay? So a range of, a viable range for our true odds ratio, for example. And it's in this way that we can use confidence intervals for hypothesis testing. Okay. The advantage of this is it's intuitive and it is couched in terms of our research problem. P-values aren't. It's a magic number. A p-value is a magic number that doesn't really tell us that much, except statistical significance. So, for example, if we are comparing a continuous variable between two groups and our confidence interval does not contain 0, then a statement of no difference is not a viable statement. We have to throw the null hypothesis away, and we can look at the effect size and gauge whether it's a clinically important effect. So we've got all of the information we need. A p-value alone does not tell us that. Alternatively, if we're considering a binary variable or a time to event variable or whatever, a 95% confidence interval of the odds ratio, the hazard ratio, the rate ratio, that does not contain 1, implies a hypothesis of no association is unlikely to be true. We can throw that away. So we still talk about statistical significance, but we can look at the effect size. Also, it gives us a little bit more information. So let's just look at very quickly, I don't know how I'm going for time here, very quickly let's just look at 4 fictitious studies. So I just made them up, so don't go and change your clinical practice based on them. Okay, we want to consider the impact of a new oral hypoglycemic agent on lowering blood sugar levels. Sorry, I'm talking about diabetes, it's my favourite disease. Okay, our outcome of interest is blood sugar control, so whether a patient can keep their HbA1c below 7% or not. And on the next slide, I'm going to give you these results in a forest plot type format. I'm going to give you the effect size and its confidence intervals for these 4 studies. I want you to consider the magnitude of the effect size. What is our estimate of the odds ratio? Is no benefit included in that 95% confidence interval? And here's some bonus points as well. Is a non-clinically important effect contained in the confidence interval as well? Okay, is it in the lower range, for example? And also, how does sample size come into play? So here's our forest plot. Sorry, it's not very big. Okay, so here's our 4 studies. In the first 3 studies, sorry, that's very small font. In the first 3 studies, the odds ratio is 4. In the 4th study, it's 1.5. Okay, so talking about these studies. Now, I want you to note this blue line here, which is what we think is a clinically important effect. And this very light grey line, which would mean an odds ratio of 1, which is a statement of no association. So let's talk about these 4 studies. In the first study, the odds ratio was 4. The confidence interval was 1.5 to 6.5. We can see that our sample estimate of the odds ratio suggests 4 times the odds of blood sugar control in the people with the new oral hypoglycemic agent relative to those not using it. Okay, we can also see that our confidence interval does not contain 1, so a statement of no association, so no differential odds, is not a viable statement. We can throw the null hypothesis away. Okay, however, One problem is at the lower range of the confidence intervals, it's conceivable that our effect size is not clinically important. Frankly, I think this is probably still quite strong evidence that the oral hypoglycemic agent works, but still somebody could argue that the real value of the odds ratio may not be clinically important. In the second study, we don't have this problem. Okay, so what we can say here is the full range of viable values for the odds ratio are all clinically important. Okay, in the third study, I'm not going to read these off the slide, I'm just going to talk about them here. In the third study, yes, we've got a large effect size from our sample, but no significant association is a possible viable value for our odds ratio. We cannot rule out no association. So we would see P as not less than 0.05 in that case. And finally, in the fourth case, we can see we've got statistical significance, but the whole range of viable values for the odds ratio are not clinically important. The sample size is clearly too large in this case. Okay, so the point here I'm trying to make is with the effect size and the confidence interval, we can say all sorts of things and we can gauge whether it's a clinically important effect. We can talk about the precision of our estimate and whether we've got a nice tight range of values. Does the lower end contain values that are not clinically important? Can we rule those out? And so on. There's a lot of information. Information a p-value alone would not give us. Okay, so just to finish off, we can see that this using confidence interval approach to hypothesis testing has some major advantages over using the p-value alone approach. Okay, and really I've already said these. We get an idea about the observed effect size, so we can gauge clinical importance. We have a viable range of values for the true population odds ratio. And by providing this extra information in our research, it allows us to get a much better feel about how statistical and clinical significance relate to each other, whether our sample size is way off, for example. We can easily spot an under or overpowered study, so where there's a big disconnection between clinical significance and statistical significance. So in doing so, gauge the quality of evidence of the study and whether it should ultimately inform clinical practice. Okay, any questions?